Okay, hi everybody, this is the second lesson in our Electromagnetism Unit in Advanced Higher Physics, and we're going to be talking about electrical potential. Now, you met potential before when we did the gravitation topic in the RMA unit, and we spoke about what gravitational potential was and being in a potential well when you're in a gravitational field. Well, electrical potential is very similar. But bear in mind that there are two types of electrical charge. So here's the definition. Electrical potential is defined as being the work done in moving a unit positive charge from infinity to a point in an electric field. Now remember, it's very similar to what we said about gravitational potential. In gravitational potential, we said it's the work done in moving a unit mass from infinity to a point in a gravitational field. So, very similar definition, only in terms of charge and in terms of a positive charge. I think we'll show you this on a little note. Right, there's an electric field around a positive charge, so arrows pointing away from it. There's a central positive charge that's producing an electric field. So if we were to bring a unit positive charge anywhere close to that central positive charge, then if we want to move that positive charge in the way, these charges are repelling. So we would have to do a positive amount of work. Work would have to be done by an external force to move that charge further into the field. And the amount of work that you have to do only depends on the size of the charge that's producing the field, that's the central charge, Q, and the location that you want to move the charge to, that's R, the distance from the centre of the charge. And we've got our constant of proportionality, 1/4 pi E naught in there as well. And because a positive amount of work would have to be done by an external force to move it further into the field, then there is a positive potential at that location in the electric field. Now the opposite then is true if we have a negative charge. If we very quickly draw a negative charge here, and we get a kind of similar scenario that we had with a gravitational field, the arrows are pointing in the way. So if we've got a negative charge and there's an electric field around that negative charge, if we bring a positive charge close to it, then we don't have to do any work at all to get that charge more into the field, because these two charges are attracting. The positive charge is attracted to the negative central charge, but an external force would be required to move the positive charge further out, in fact to move it to infinity where the potential would be zero. So in this case, the electrical potential would be equal to, it's still Q over 4 pi E naught R, where Q is the size of the central charge and R is the distance that you are from that charge, but it will be a negative potential because you have to do work to move it out of the field, not into the field. So there is a minus sign, a negative potential at a location in an electric field around a negative charge, and there will be a positive potential at any location around a positive charge. So if electrical potential is the work done in moving a unit positive charge from infinity to a point in an electric field, it should be measured in joules per coulomb. But you may remember from your higher work that joules per coulomb is the same as volts. And we can use volts for electrical potential. And that electrical potential only depends on the size of the charge producing the field and the distance of your location from the centre of that charge that's producing the field. Now, remember, electrical potential is measured in volts, and it can either be positive or negative depending on the sign of the charge that's producing the field. Now, the equations for electrostatic force, electric field strength and electrical potential are very similar to the equations you've already met for gravitational force, field strength and gravitational potential. It's the same equations, but with different quantities and different symbols in them. Here's a table with all those relationships in it. Now, it looks pretty frightening, but just to see the similarities between the relationships on each row, the first row are the force equations. Gravitational force, gmm over r squared. Look at the electrical force. kqq over r squared is charge instead of mass, different constant. And if we substitute in the 1 over 4 pi e naught for the constant, then we get the same relationship in a slightly different format. Now for each row there, for field strength, for potential, and for potential energy, you can hopefully see the similarity between the relationships and how you would move from one relationship to the next. Now all of those relationships are on your relationship sheet, with the exception, I think, of the potential energy ones, which you should be able to derive. So let's have a look at electrical potential energy. Now, if we've got a relationship for the electrical or electric potential at a location somewhere in an electric field, then the electrical potential energy of a charge at a location in an electric field is given by this relationship. So potential energy will be equal to the electrical potential V times the charge that you place at a location in an electric field. Remember W equals QV from higher physics? Well, this is really the same thing. You have to do work to move a charge in an electric field. Energy has to be transferred when you move a charge from infinity to a place, to a position, to a location in an electric field. So if we take our electrical potential relationship, which is Q over 4 pi E naught R, we multiply that by a charge that we place at a location that's got that electrical potential, then we get the potential energy of a charge placed at a location where there's an electrical potential. So we get QQ over 4 pi E naught R. And don't forget, you can still use that shortcut of 9 times 10 to the 9 for 1 over 4 pi E naught. The potential energy relationship is not on your relationship sheet, but you could get asked about it in a problem solving question. So as long as you know that potential is the work done in moving a unit positive charge from infinity to a point in an electric field, then you can apply that to any charge that is placed at any location in an electric field. For example, if we wanted to calculate the potential energy of an electron in a hydrogen atom, if the radius of the electron's orbit is 5.3 times 10 to the minus 11 meters, then we know what the charge on the electron is, we know what the charge on the proton is that's in the hydrogen atom, so we can work out the potential energy of that electron. Let's show you that on a wee note. Right, so here's my hydrogen nucleus, that's the proton that's at the centre of the hydrogen atom, and there's my electron orbiting around it, and that electron is orbiting at a radius of 5.3 times 10 to the minus 11 meters. Now, the charge in the middle we'll call Q1, that's the charge that's producing the field, that's the proton. Q2 is our electron, and therefore the potential energy of that electron will be the charge Q2 times the electrical potential at that location. Now that electrical potential is Q over 4 pi E naught R, and that's a positive potential because it's an electric field around a positive charge. So we know what Q1 is, we know what R is, and we can work out that positive potential. So the potential energy of the electron though will be Q1 Q2 over 4 pi E naught R. Or of course you could still use the shortcut of K instead of 1 over 4 pi E naught, where K is equal to 9 times 10 to the 9. Now our Q1 is the charge on the proton, which is 1.6 times 10 to the minus 19. Our Q2 is also 1.6 times 10 to the minus 19. So Q1 and Q2 are the same, although we should really put in minus 1.6 times 10 to the minus 19 for the electron. And we know that radius, the radius was given to us of 5.3 times 10 to the minus 11. We've got all the numbers we need. we can now work out that potential energy. So there's all my working then. The constant of 9 times 10 to the 9, Q1 times Q2 is our 1.6 times 10 to the minus 19 squared, divided by the radius of the electron orbit, gives us our value of potential energy of minus 4.3 times 10 to the minus 18. Why is it negative? Well, it's a positive potential around a positive charge, but we are placing a negative electron in that field. So work would have to be done by an external force to move it out of the field towards infinity where the potential is 0. This is a kind of similar scenario to gravity. Gravity is always attractive, and therefore gravitational potential is always negative. You have to do a positive amount of work by an external force to move it out of the field towards infinity where the potential is 0. Now, we can take that one stage further and talk about the ionization of the hydrogen atom. This is not in the course, but it's for interest only, and you may have asked this question last year when you were doing higher physics and we were talking about the energy levels of the electron in the hydrogen atom, and you get a diagram that looked like that, where your bottom state, the ground state, had a value of something like minus 2.18 times 10 to the minus 18 joules. In fact, more often than not, it was minus 21.8 times 10 to the minus 19 joules. So in order for that hydrogen atom to be ionized, for the electron to escape from the atom, we would have to give it at least 2.18 times 10 to the minus 18 joules for the electron to jump from the ground state and then reach the ionization level, the top level where the energy is 0. But the big question is, why do those energy levels have those values? Where do those values come from? Well, those energy level values are all to do with the radius of the electron orbit when it's in its different energy levels. So for example, the electron in the ground state in a hydrogen atom orbits at a radius of 5.29 times 10 to the minus 11 meters. Now, it's got electrical potential energy due to its location in the electric field, but it's also got kinetic energy due to its tangential velocity of its motion in its circular orbit. So could we show that the total potential energy plus the kinetic energy of the electron in its ground state is minus 2.18 times 10 to the minus 18? That's the number that's shown on the bottom of the diagram on the right hand side there. That's the total energy of the electron in the ground state. Now that is the actual value. So could we work that out based on the fact that the electron is orbiting at a radius of 5.29 times 10 to the minus 11? Yes, we can. It's only for the brave. It's on the next slide. So here we go. Remember, the electron has both potential and kinetic energy. It's going to have negative potential energy. Remember, because you'd have to do work to move it out of the field to get it up to the 0 of its electrical potential. So the electrical potential energy relationship is there, minus Q1 Q2 over 4 pi E naught R. And we can derive a relationship for the kinetic energy of the electron, and we have to go back to our knowledge of central force again. The electron is orbiting around the nucleus of the hydrogen atom. It's moving in a circle. So the central force is provided by the electric force. So Fc equals Fe. Remember, central force mv squared over r. And the electric force is kq over r squared. Or Q1 Q2 over 4 pi E naught r squared. Now we can do a little bit of simplification here. We can cancel out one of the r's on the bottom, and if we divide both sides by 2 as well, we will get kinetic energy on the left. So a half mv squared, remember we're cancelling out one of the r's on the bottom and dividing by 2 on both sides, and we end up with, on the right hand side, Q1 Q2 over 8 pi E naught r. That would be the kinetic energy of the electron in any particular orbit that's at an orbit distance of r. Q1 and Q2 is the charge on the electron and the charge on the proton at the nucleus. So the total energy then, if we've got kinetic energy and potential energy and we add these both together, EP plus EK gives us the potential energy relationship on the top left plus the kinetic energy relationship on the bottom right. And when we add them together, it's basically minus a quarter plus an eighth. And minus a quarter plus an eighth gives you minus an eighth. So my penultimate line there, my second last line, has got minus Q1, Q2 over, it's effectively 1 over 8 pi E naught R. That's the total energy of the electron in the orbit that includes its potential and its kinetic energy. And if you substitute in all the values for the hydrogen atom, so charge on the proton, charge on the electron, and the radius of 5.29 times 10 to the minus 11, pop it all into your calculator, it gives you that value for the ground state in the hydrogen atom of minus 2.18 times 10 to the minus 18 joules. Now remember, that's beyond the scope of this course, it's for interest only, but it shows you, maybe shows you where these values have come from in diagrams that maybe you've seen last year. Now a little word about scalars and vectors, because it's quite easy sometimes to get mixed up between positives and negatives for directions, positives and negatives for arithmetical operations, you know, adding and subtracting, and positives and negatives for types of charges, names of charges. So in simple terms, force is a vector, energy is a scalar. So electric force is a vector, direction matters. Electric field strength is a vector, because field strength is the force per unit charge. So it's a vector. But electrical potential is a scalar. It's the work done per unit positive charge. Work done is energy. Energy is a scalar. Electrical potential energy is a scalar. So first two, vectors. Second two, scalars. It's important then to remember this when you're dealing with situations with multiple charges that you might need to add together, but you have to add them together using vectors. It's also important to remember that although electrical potential is a scalar, electrical potentials could be positive or negative depending on the nature of the charges, and you should therefore take care when you're adding them. I think a few examples might make this a bit clearer. Right, here's the past paper question from the 2016 paper. This is question 13. So it says 13a, Q1 is a point charge of 12 nanocoulombs, plus 12 nanocoulombs. It's a positive charge, so positive potential around that charge. Point Y is 0.3 meters from Q1 as shown in figure 13a, and we have to show that the electrical potential at point Y is plus 360 volts. Now it's a show question. If it's a show question, you have got to go straight to your relationship sheet and pick out the particular relevant relationship for this part of the question. So electrical potential, you can't use the shortcut in this case, you have to use the one as it appears on your sheet. So there it is, V equals 1 over 4 pi E naught times Q1 over R. Now we know what Q1 is, it's plus 12 nanocoulombs. We know what R is, it's 0.3. Substitute them in, but make sure you substitute in the permittivity of free space from your data sheet. It is a show question. You're not getting 1 mark for the final answer because it's given in the question. You're getting the second mark for substituting in all the values correctly. So 1 over 4 pi times the permittivity of free space, 8.85 times 10 to the minus 12, times your Q1 on the top there is 12 nanocoulombs over 0.3 meters. Pop that in your calculator and you get an answer of 360 volts. It is positive, although the positive sign's bracketed in the SQA marking scheme there. So 360. Part B, a second point charge Q2 is placed at a distance of 0.4 meters from point Y, and the electrical potential at point Y is now 0. And in B part 1 we have to determine the charge of Q2. Well, there's a 3-mark question. Q2 must be a negative charge, because if we want a total potential at point Y to be 0, and we've already got plus 360 volts, then the potential at point Y due to charge Q must be minus 360 volts. So if we substitute that in, we're going to use the same relationship again for potential, but this time our potential will be minus 360, and we're going to sub in the value for the new distance R and hopefully be able to work out Q2. So here it's here, part B, part 1. So our potential is minus 360. Same relationship, substitute in the minus 360 and rearrange for Q2, and we get a value for Q2 of minus 1.6 times 10 to the minus 8 coulombs. Part 2, B part 2. Now this is pretty tricky. It says determine the electric field strength at point Y. Remember, electric field strength is a vector. If we were to put a positive charge at point Y, what would happen to it? Well, it would be repelled away from Q1, because a positive charge will repel a positive charge, but it will be attracted to Q2 because Q2 is negative. So the effect of both of those electric fields is in the same direction. So therefore, although the charges are opposites, the vectors are in the same direction. The electric field acting at point Y due to Q1 will be to the right, and the electric field due to charge Q2 will also be to the right. So whatever those electric field strengths are, we're going to add them together. Let's have a little look at the SQA marking scheme here. We've picked the electric field relationship from the relationship sheet, 1 over 4 pi E naught Q1 over R squared. Now you could have used the shortcut here if you wanted, because it's not a show question, but we substitute all the values in for the electric field due to charge number 1, and we get 1200 newtons per coulomb to the right. Remember, electric field strength by definition is the force per unit positive charge, so that force would push a positive charge to the right. If we work out the electric field strength due to charge number 2, and you substitute all the values into the electric field strength relationship, you get 900 newtons per coulomb, but that will also be to the right because Q2 is negative and it will therefore attract a positive charge that's placed at point Y. So if we add the two of them together, the vectors are in the same direction. So 1200 plus 900 gives us 2100 newtons per coulomb to the right. 4 marks. That's pretty difficult. Make sure you try a few examples. There's all the relationships again. Don't forget they're all on your relationship sheet. Just make sure you're familiar with the quantities, with the symbols for the quantities, and with the units and the abbreviations of those units for each quantity as well. And gravitational potential and potential energy are always negative. Remember, you have to do work to get up and out of the field. Electrical potential and potential energy can be either positive or negative. It depends on the sign of the charge that's producing the electric field. That's it. See you in the next one.